The Pythagorean theorem is one of the most useful tools you'll ever learn, mostly because you just use it so often. You can't get through algebra, geometry, trig, or even calculus without it. And in this video, we're going to be talking about everything related to the Pythagorean theorem, including what it is, why it actually works, and how you can use it in real life. So what is the Pythagorean theorem? Well, first of all, it's a theorem that only works for right triangles. It doesn't work for obtuse triangles or acute triangles, and we'll talk about that more in a bit. It can only be applied when you have a right triangle. Let's remember that a right triangle is a triangle with one 90-degree angle, which we indicate here with this little box in one angle of the triangle. So this little box means that it's a 90-degree angle. And when a triangle has exactly one angle that measures exactly 90 degrees, so not 89, not 91, but 90, that is a right triangle. And the Pythagorean theorem only works for right triangles. So we have one angle that's 90 degrees. It doesn't matter the value of the other two angles. They could be anything. As long as one angle is 90 degrees, it's a right triangle, and we can apply the Pythagorean theorem. So under those circumstances, what does the Pythagorean theorem state? Well, it's a relationship between the length of each side of this right triangle. So if we were to call the length of this side A, if we called the length of this side B, and if we called the length of the hypotenuse, which remember is always the longest side, and it's always the side that's opposite your 90-degree angle. So if I find my 90-degree angle and I go straight across to the other side of the triangle, that is the hypotenuse. It's the longest side. So if we call the hypotenuse C, then the Pythagorean theorem says that if I take the length of side A and I square it, so I get A squared, and then I add to that B squared, so I take the length of side B and I square that, and I get B squared. When I add these two things together, that will always be equal to C squared, the length of the hypotenuse squared. And the Pythagorean theorem and right triangles are inextricably tied together. They're always a pair because the Pythagorean theorem works for every single right triangle you will ever find. It doesn't matter what the length of side A is, or the length of side B, or the length of side C. If it's a right triangle, then the Pythagorean theorem, A squared plus B squared equals C squared, will always be true. And normally when we talk about the Pythagorean theorem, we like to think of it as starting with the triangle, and then the Pythagorean theorem is a result. In other words, sort of this logic that if we have a right triangle, if we have a triangle with a 90-degree angle, then we know that the Pythagorean theorem is going to be true for that triangle. But we can sort of think of it the opposite way too, and this is the converse of the Pythagorean theorem. The logic is basically the opposite, which says that pretend I don't have this triangle at all right now. I just know that I have a triangle and I'm calling the sides A, B, and C. Well, if I know for that triangle that A squared plus B squared equals C squared, then I automatically know that I have a right triangle, that the triangle is a right triangle. So you can sort of start with this theorem and conclude that you have a right triangle, or the opposite way, know that you have a right triangle up front and conclude that this theorem has to be true. So the Pythagorean theorem is that given a right triangle, I know that A squared plus B squared is equal to C squared. The converse of the Pythagorean theorem is if I know that A squared plus B squared equals C squared, then I know that I have a right triangle. Now remember before we talked about acute and obtuse triangles. This is a right triangle, but at the most broad level, there are three kinds of triangles: a right triangle with a 90-degree angle, an acute triangle, and an obtuse triangle. In an acute triangle, the largest angle is less than 90 degrees. That might look something like this. All three of these angles in this triangle are less than 90 degrees, so this is an acute triangle. Or you can have an obtuse triangle where the largest angle is greater than 90 degrees, and that might look something like this. The largest angle in this triangle is this angle here, and it's larger than 90 degrees. So you have an acute triangle, a right triangle, and an obtuse triangle. And the Pythagorean theorem is sort of a midpoint. It says that in a right triangle, a squared plus b squared is exactly equal to c squared. Well, when we have an acute triangle, we know that a squared plus b squared is going to be greater than c squared. And when we have an obtuse triangle, we know that a squared plus b squared is less than c squared. So you can almost think of this like the Goldilocks story, where everything is either too small, too big, or just right. In an acute triangle, a squared plus b squared is bigger than c squared. In an obtuse triangle, a squared plus b squared is less than c squared. But just right, in the middle of those, is the right triangle, where a squared plus b squared is exactly equal to c squared every time. And that's why Pythagorean theorem is only for right triangles, because if your largest angle is less than 90 degrees and you have an acute triangle, then this inequality gets skewed one way. If your largest angle is greater than 90 degrees and you have an obtuse triangle, the inequality gets skewed the other way. Pythagorean theorem is only for right triangles because it's only when you have that 90-degree angle that this equation happens to be exactly spot on, and a squared plus b squared will in fact equal c squared. So how does the Pythagorean theorem actually work? Well, let's go ahead and walk through a proof together. We'll actually do the proof that Pythagoras himself used when he proved this theorem. Pythagoras was a Greek mathematician and philosopher who lived between about 570 and 500 BC, and he's actually thought to be the first person to write down the proof of the theorem, but people had knowledge of it and were using it long before Pythagoras lived, including the Babylonians as early as about 1900 BC or so. So why is the Pythagorean theorem true? Well, let's try to prove it right now. If I have two squares, and these are identical because I just copied one and pasted it, so these have exactly the same area and the same dimensions. They're both the same height and the same width. So if I draw a vertical line in this first square, and I can actually draw this anywhere, but let's say I do it here, and then I make a perfectly horizontal line, maybe about here, such that this little square is a perfect square, and this larger square is a perfect square. And then I want to go ahead and bisect these two rectangles here so that I split them both into two triangles. Now at this point, I have these four triangles, and I want to go ahead and look at one of them. So if I look at this triangle right here, I can see that it's a right triangle because this is a perfectly horizontal line, and this is a perfectly vertical line, which means that this is a right triangle with my 90-degree angle right here. So I've got a right triangle. I can call the length of this side of it A, and the length of this side B. That means that this perfectly symmetrical triangle that's sitting on top of it, it's the exact same dimensions, it's just flipped over. This has dimensions here, A and B as well. Now remember, this little square is a perfect square, so I know this is A by A. I know the length of all of its sides are A. And this is also a perfect square, so I know that the length of all of the sides of this square are B. Which means that when I look at these other two triangles here, I can see that the length of this side is B, I already know that, and the length of this little side then is A, based on the length of, or the width of, this square up here. So this is also A, and this triangle right here on the right, this is A times B. So notice here that by Pythagorean theorem, I have four triangles. The length of the legs are A and B, and the length of the hypotenuse I can call C. So this is C and C, obviously, and then C and C here. Now, how do I prove that a squared plus b squared equals c squared for one of these triangles? Well, if I take the size of this triangle, one of these triangles, and I translate it directly over into this other square here, then my triangle looks about like this, and I can actually draw four of these around the edges of the triangle that have the same dimensions as the one in the triangle on the left. So all four of these triangles around the outside, I can now say have dimensions A and B here, A and B here, A and B here, and A and B. I also know that the length of each hypotenuse of the triangle is C, which I get from this other square. So I can say C, 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 and C. Now I just need to add up the area of each full square. So if I look at the square over here on the left, I know I have this little square, A times A, so the area of this small square is A squared. So I get A squared. The area of this large square is B times B, or B squared. The area of each triangle, remember the formula for the area of a triangle is 1/2 times the length of the base times the length of the height. So that would be 1/2 times B times A, or 1/2 times A times B. And I have 4 triangles, so I want to say I have 4 triangles, and the area of each one is 1/2 AB. Now over here on the right, I have the area of the square in the center, which is C times C, or C squared, so I get C squared. And then I know that the area of each triangle, first of all, I have 4 of them, so I want to say total area is 4, and then the area of each triangle is 1/2 times A times B. And I already know the area of these 2 squares is equal. So if I were to set these equal to one another, I have a 4 times 1/2 times AB on each side. So I could subtract that out from both sides, and these values would cancel away completely. And then all I'm left with on the left side is A squared plus B squared, and all I'm left with on the right side is C squared. So I know by this proof that A squared plus B squared must be equal to C squared, and that's how Pythagoras himself proved that the Pythagorean theorem was true for right triangles. So now the last question that remains is, how do we actually use Pythagorean theorem, and how can it be used in real life? Well, its most common and simple application is just finding the distance between two things when those things are on a diagonal. For example, let's pretend that I need to do some roofing work on my house. I need to get up on the roof and make some fixes to the roof, and I need to know how long of a ladder I need to get in order to reach the roof. That's a simple problem that I can actually solve with Pythagorean theorem. So let's pretend that this is my house with my roof on top of it, and I need to be able to reach to this point right here from my ladder on the ground. So if I say, for example, that this has to be what my ladder looks like, how do I figure out how long the ladder needs to be in order for me to reach the roof? Well, it would be difficult to calculate the length of this diagonal or to measure it through space. If I tried to take a measuring tape and measure this distance, that would be very difficult. What would be much easier is if I could recognize that this is just the hypotenuse of a triangle. So instead, I construct a triangle and I go here parallel to my house and then along the ground, like this, and I know right away that since I have this distance level along the ground, and I have this distance, which is perfectly vertical, that this is a right triangle because these two lines are perpendicular. This is perfectly vertical, perfectly horizontal, which means this is a 90-degree angle, and this is a right triangle, and that means that because it's a right triangle, I can use Pythagorean theorem. Let's say that I already know that my house is 12 feet tall, which is maybe a safe assumption because I know how far it is from the floor to the ceiling in my house. So let's say I know that this is 12 feet here. And let's say I want to place my ladder, the base of it, 5 feet away from this point here. I could easily measure that with a measuring tape along the ground, and so I could say that this is 5 feet here. Now I can easily use the Pythagorean theorem to find the length that the ladder needs to be to reach this point. So again, this is my hypotenuse. It's the longest side across from the 90-degree angle. So then I can use Pythagorean theorem and say that I want to square this side. So I want to say 5 squared. I know that by Pythagorean theorem, when I add that to the square of this side, so 12 squared, that has to be equal to the length of the hypotenuse squared. That has to be equal to c squared. And now here's how I solve this for c. I take 5 squared is 25, so 25. I take 12 squared is 144, and then I have c squared. 25 plus 144 is 169. Now, in order to solve for c, I need to take the square root of both sides. So I want to take the square root of 169 and the square root of c squared. Now, the square root of c squared is c, and the square root of 169 is either positive 13 or negative 13. But remember, with Pythagorean theorem, we're always dealing with right triangles, and it's impossible for the length of any side of a triangle to be negative and for that triangle to still exist. So we can always ignore that negative value, and we can say that c is equal to positive 13. Therefore, I know then that the length of my ladder has to be 13 feet in order for me to safely reach from the ground to the corner of the roof if I place the base of the ladder 5 feet away from the house. The other great thing about Pythagorean theorem is that you can use it to solve for any side of the triangle. So in this real-world problem, we did not know the value of the hypotenuse, but we knew the value of the other two legs of this triangle. But let's say that instead, we already knew that the ladder was 13 feet long, and we already knew that the height of the house was 12 feet, and we wanted to know how far away from the house we could place the base of the ladder. In other words, how far can this distance be? Well, instead of this equation here, this would be our unknown value, so we would call that a, and we would say a squared. We already know 12, so we would say 12 squared, and then we already know the length of the ladder is 13. And then we could solve this for a by saying a squared plus 144 is equal to 169. Then we would subtract 144 from both sides, and we would get a squared is equal to 25. And then we would take the square root of both sides in order to solve for a. So the square root of a squared is a, and the square root of 25 is positive or negative 5. But again, remember that because we're dealing with a triangle, we have to have a positive distance, so we can forget about the negative value and just say positive 5. So it doesn't matter which two sides of the triangle you have. You could have 5 and 12, you could have 12 and 13, or you could have 13 and 5. If you just plug them in to the correct places in the Pythagorean theorem formula, you'll always be able to solve for the length of the third side. We'll talk about one more thing as it relates to the Pythagorean theorem, and that is what's called Pythagorean triples. Pythagorean triples are sets of 3 integers that satisfy the Pythagorean theorem. So in a lot of cases, you'll be given 2 values, let's say, for example, the values for a and b, and you'll need to solve for the value of c. Well, when you plug those things into the Pythagorean theorem and you solve for c, you'll end up with either a decimal or fraction value for c. It won't be a perfect integer. It won't be a whole number. Same thing goes if you're trying to solve for one of the other side lengths. There are an infinite number of values that satisfy the Pythagorean theorem for a, b, and c, but not every set is going to be 3 integers where a and b and c are all positive whole numbers. A Pythagorean triple, on the other hand, will be 3 integers, 3 positive whole numbers, that satisfy the Pythagorean theorem. The simplest and most famous one, if we have values here of a, b, and c, is the set 3, 4, 5. Now there's a couple of things to keep in mind about Pythagorean triples. The first is that a always needs to be what we call the opposite side. A is always, first of all, the shortest side in the right triangle. So C is always the hypotenuse, the longest side, and the side that's across from the 90-degree angle. And then you have the other two legs of the triangle. And the shortest leg, the shortest side, is always going to need to be A. So if we keep that rule and we say A is always the shortest side, then when A is 3, the shortest side is 3, then B, the other leg, is 4, and C, the hypotenuse, is 5. And we can see that if we plug this into the Pythagorean theorem, that this set of values satisfies the Pythagorean theorem, because we get 3 squared plus 4 squared equals 5 squared. And when we simplify this, we get 3 squared is 9, 4 squared is 16, and 5 squared is 25. 9 plus 16 is 25. So we get 25 equals 25, and we can see that the set 3, 4, 5 satisfies the Pythagorean theorem because this equation is true. Now, the cool thing about Pythagorean triples is that you can pick any odd number for A. So 3, 5, 7, 9, 11, etc. Any odd number, and you will have a Pythagorean triple. Now, it's important to say that you can pick a value for B or C. For example, if I have a value of 5 for A, the shortest side, I can then pick any value for B that's greater than 5. Since A is the shortest side, B has to be larger than that. I could pick a value for B, and C would not necessarily be a positive whole number. For example, if I picked B equals 6, I would not get a positive whole number for C, so that would not be a Pythagorean triple. It's just that a Pythagorean triple is possible. There is one possible Pythagorean triple for every odd value of A. Here's how you find the specific Pythagorean triple for every odd number A. B is always going to be A squared minus 1, all divided by 2. And C, the hypotenuse, is always going to be B plus 1. So that's a lot right there. So what do we actually mean by that? Well, here's what it means. Let's dissect one of these. Let's take 5. Remember, we can pick any positive odd whole number for A, so 3, 5, 7, 9, 11, 13, 15, any odd number for A, the shortest side, and we know we're going to come up with a Pythagorean triple. So let's say we pick 5, and now we want to know what B and C are that match for that Pythagorean triple. Well, we take the value of A, 5, and we plug it into this, A squared minus 1 over 2. So what we get there is 5 squared minus 1 over 2, which is equal to 25 minus 1 in the numerator. Well, 25 minus 1 is 24, and then 24 divided by 2 is 12, so 12. And then to get the value for C, all I need to do is take B and add 1 to it, because the formula for C here is B plus 1. I know B is 12, so 12 plus 1 is 13. So my Pythagorean triple for A, B, and C is 5, 12, 13, which should look familiar because remember, this was the Pythagorean triple we used in the last problem where we were talking about the ladder leaning up against the house. So because these are 3 positive whole numbers, they're integers, they form a Pythagorean triple. And I could do the same thing with any other positive, odd, whole number for A. So 7, 9, 11, etc. I could create a Pythagorean triple using these formulas. I hope that video helped you, and if it did, hit that like button, make sure to subscribe, and I'll see you in the next video.